Hi everyone, my name is Cargo Ann Treasure and I'm going to discuss the multimodal acoustic electrical feature extraction framework for machine learning based partial discharge classification under the group code SWML4. So I'm going to discuss all the models that we trained, plus the compression strategies and the deployment. So we shall begin with a simple introduction to partial discharge. Partial discharge is a localized insulation breakdown in high voltage systems. This occurs due to a small spark that can lead to the breakdown of insulation. And once this insulation breaks down, it can lead to hazards such as fires and also safety concerns. So with the problem statement, we aim to cater to this problem via machine learning in order to perform predictive maintenance and in order to extract the different types of partial discharge. So our three tasks mainly will be focusing on the partial discharge detection, classification, and the localization. So our research questions, we had two datasets mainly. We had an acoustic and an electrical datasets. Within these datasets, we aim to check whether the dataset was complete to extract the different features that would further aid these three tasks. So what we did was to validate the dataset suitability for multimodal classification and source localization. We performed detailed exploratory analysis besides building these 13 models. Our contributions were included building the 12 models plus a 13th model that combined two of the models from the 12 models, and we cleaned these data sets, and we also did a semi-supervised multi-fusion model that classified the partial discharge. So this was our system architecture. Our system architecture included extracting the features from the SFTC CT that extracted electrical signals, and the microphones that extracted acoustic signals. We had a neural layer, the pulse detection, the feature extraction. We end up with a causal layer, the symbolic layer, and also an agentic layer that would provide explainable output plus the final output. So as I said, description and expression analysis, we looked at the acoustic data set, which included it was a large data set that was collected from 32 sensors, microphone sensors across 90 locations, and each recording was sampled at 96 kilohertz. The electrical record discharge datasets included the three different types of partial discharge, which was corona, surface, and internal. While the acoustic dataset did not necessarily differentiate the types of partial discharge, rather it looked at the noise and the partial discharge and the traps. So the users of each of these datasets, for the acoustic was mainly to detect partial discharge, say from noise, then the acoustic was mainly to classify the different types of partial discharge. So right now I'm going to talk about all the models. So let's begin with the light GBM. The light GBM model, we had three experts. The light gradient boosting model, we had three expert models in this, where we had a signal classifier that was used on the acoustic data, which was used to detect the partial discharge. We had a localization model to localize where the partial discharge came from, and the electrical model that was mainly using the electrical features. So these were combined. The results of these models were combined into a meta matrix that was input into a fusion model that was able to predict the type of partial discharge and also the location where the partial discharge is coming from. However, this model was a bit unstable, and that's why we didn't use it finally. So the next was a partial discharge localization model. What it used was the scalograms. It had three branches. One was a CNN branch, the physics, and the physics branch was to also ensure that the predictions met the real world physical constraints. So the outputs of these two branches were put into the fusion and localization head and used to predict where the partial discharge was coming from. However, this model did perform well because scalograms don't necessarily carry information about the location or the speed of sounds. They are images. So we had the partial discharge symbolic the symbolic model. So what it did, it had also the 3 branches, just as the PD localization model. So it took in the scalograms and the physics features, and they were put into the 3rd branch, which was a multimodal fusion branch. With this model, we used the 3-dimensional CNN model to capture the quality of the acoustic features, and we also had an excitation and squeeze and excitation layers that were used to pay attention to the most important features. So these were fed into the multimodal fusion layout, and were able to output the 3 different types of classes. So this was mainly in classification between partial discharge, noise, and chaps. So we had also an autoencoder architecture. The use of this model was mainly was used on the partial discharge acoustic data only. It was used to identify the different clusters of the partial discharge, which would further inform the different, which was further used to produce pseudo labels that were used to classify the unlabeled partial discharge data. So with this model, mainly we used the autoencoder architecture, which was an encoder that compressed this data into a 128-dimensional vector, and the decoder that reconstructed the image. So it used mainly reconstruction. With the conformer used the pseudo labels from the autoencoder in order to classify the different types of partial discharges from the unlabeled partial discharge data. It used mainly the CNN transformer to extract the features, and the transformer in order to pay attention to the most important features. Next was the SIMC LR light model. What this model used, remember in the autoencoder, it was mainly reconstruction to see if we could reconstruct the original signal, but with this it was mainly comparing the different types of signals in order to find the similarities and cluster them accordingly using the k-means. So it was a different approach to the autoencoder in order to produce these pseudo labels, or these different unsupervised clusters. So with the temporal MC pyramid model, what this model used, it was extracted the MFCC features from the acoustic sound. So these are features of signals and the derivatives. So after extracting these derivatives, we split the audio into the 3 stages, and then we used the Gaussian mixture model in order to cluster these models on using the probability of belonging to a particular cluster. However, it produced like a fewer clusters, and the silhouette was a bit low. So it acted as a baseline for the rest of the models in terms of clustering. So the next model was the phase, the PRHMM, which was it used mainly the pulses. From these pulses, you could detect the phase angles of these pulses. So you were able to group these pulses from the electric signals into the phase bins, and we used the hidden Markov model in order to extract more features. And at the later stage, we used the random forest classifier model in order to classify the different types of partial discharge from the electrical signal. So this model used mainly the electrical signal using pulse detection, phase extraction. So here for this model, it was the ecostate network model. So what it does mainly, it extracts the partial discharge signals, and then it stores this information in a reservoir. So it's used mainly to capture the temporal characteristics. You know how the waves travel through time. So it captures the past behavior of the waves. So after capturing this past behavior, after capturing these past behaviors and the features, they are put into a ridge regression classifier So with this classifier, we're able to classify the different types of partial discharges. What this reservoir helps in, it enables the model to easily remember the past behavior without requiring further retraining. So that was the use of the reservoir. So with the multimodal GPC localization, you see that it had different branches. We had the branch that took in the electrical signals that provided the different types of partial discharge, and the branch that took in the acoustic signals that provided the location of the partial discharge. So when these branches were combined into the fusion branch, we're able to tell the different types of partial discharge and the location of where the partial discharge took place. However, this model was a little unstable due to the difference in the domain, given that this is electrical and have acoustic. So that the next model was the spatial temporal graphical neural network, the CTGNN. What it does mainly is predict location and detect the partial discharge. It uses a graphical neural network with a message passing to see with the nodes being the 32 nodes that represented the 32 microphones that were used in detecting these acoustic sounds or the signals. So this information was passed through the attention heads, and we used the message passing in order to learn different information that was captured by the different nodes, and we later passed through the classifier and the localization head in order to classify, to detect the partial discharge and also detect where it's coming from. So we had the GPC model. What it used mainly was probability. It was mainly using the probability in order to determine the different types of partial discharge. So this model, the CTGNN, detected the partial discharge from noise, while this model was used to tell the type of partial discharge that was detected. So here we used we process the signals, use wavelet scattering in order to extract the signal, to extract features. Then we use a Gaussian process classifier, which uses probability in order to tell the different types of partial discharges. So these two models were then combined to form a fusion model, whereby the GPC model was teaching the CTGN model in order to tell the type of partial discharge that has been detected by the CTGN model. So with this model, we're able to tell the different types of partial discharge from the acoustic data, mainly using the pseudo labels. We also use the cluster. So what we did was to use the clustering in order to tell the different types. We clustered the embeddings from the GPC model that gave information about the different types of partial discharge, and we were able to match them to the unlabeled acoustic data. So we then passed through the PD type head that was able to predict the type of partial discharge from unlabeled acoustic data. It used semi-supervised learning. So with the results, we see that the corona type struggled mainly in the recall, and we see the internal struggling mainly in the precision, as you can see here. But the accuracy, we received an overall accuracy of 86% from the fusion model. So the explainable AI results reveal why we got these results. So you can see that in class 1, which is the internal, you see that its embeddings were scattered between the internal and the surface, and that's why you can see the results. You can see that it was difficult to detect the internal and the coronal discharge. So here in these graphs, we see the nodes that were activated in detecting the different types of classes. So the first one was corona. These were the nodes activated, the internal and then the surface. So that graph shows the nodes that were activated when corona was misclassified as internal. So these were the nodes that were activated. The other graph shows the different confidences in predicting the different types of classes. So we go to the deployment pipeline. Our deployment followed the cloud principles. It was deployed mainly on the cloud, whereby we had a front-end UI and we used the Flask API. We sent the request to a Flask API. So these audio sounds were then pre-processed and fed to the CTGN model that was able to detect the partial discharge. So once partial discharge is detected, it's then sent to the CCGN model. Remember, it's a fusion model with a GPC model in order to detect that type of partial discharge. So this was our interface, an interface mainly that took in acoustic sounds and was able to detect whether there was a partial discharge in this acoustic sound, and if partial discharge is detected, it is then sorry about that, it is then classified to the type of the partial discharge. So we go to the model compression. We employed three main techniques of the compression, which was knowledge distillation, pruning, and quantization. Knowledge distillation, we trained a student model, and we're able to reduce the model size from 540 to 86 kilobytes. So mainly with this student model, we're able to reduce the number of heads to half, the attention heads, but however, this affected the accuracy, the localization accuracy. Since less attention was paid in order to take the features that could capture, since localization needs a higher attention in order to capture the changes or the features that are required. So the next was quantization. So quantization is mainly predicting. We reduced the way the weights were being stored. So the weights were stored in large, as the large 42 float 32 figures or data. So we had to reduce the size of the weights to the int 8 data. So mainly mainly what it does, it reduces say the precision, the precision of the weights in order to reduce the size of the model. So with this, we're able to attain a 33% reduction in the model size. Next, the best performing model was mainly done using structured pruning, where we reduced all the dimensions. We have the dimensions, and in all the stages from the message passing to the different classifier heads. After having these dimensions, we realized there was no difference in the accuracy and in both the localization and the classification. So we reduced the parameters by 74% and the model size reduced by 73%. So we see that structured pruning was able to produce a model that with little change in performance. So with our conclusions, we see that we see the use of the graphical neural networks, especially in classifying and detecting where the partial discharge is coming from, and the Gaussian process classifier in classifying the different types of partial discharge. So our limitations are mainly in pseudo-label noise, imbalanced and small test data sets, and also one instance we aim in improving the pseudo-label qualities and getting a larger, more diverse data sets and edge optimization. So we acknowledge the Dataport datasets, the Science Direct publication that informed this research, and Mr. Galiwango for guiding us in the machine learning. Thank you so much.